Hello everyone, this is our MAE 152 project where we will analyze several components found on the UCI electric race car. The race car must endure several dynamic events during competition, which introduces different load cases on our components. We will be analyzing the chassis, brake rotor, suspension upright, battery box, and powertrain hub on the car. The type of analysis will be specific to each part depending on the use and loads applied to it. The first component we will analyze is the chassis, which connects all the car systems and protects the driver from harm while racing. The chassis is made of 1020 steel of varying thickness and bears a weight of 800 pounds, which includes all system components and drivers, distributed 52-48 front. We simulated two scenarios. The first scenario is hard linear braking, and the second is head-on collision with a wall without an impact attenuator. Linear braking is modeled by loading the wheels with model of trusses with 1G per tire, while the collision is modeled by adding a 5G load to the front bulkhead. Heavy components such as drivers, batteries, and motors were modeled to continue moving forward as the chassis comes to a hard stop to simulate a more realistic load. We created 3 revisions from the original, each reinforcing a separate part of the car, which addresses points of concerns found from the original simulation. Revision 1 reinforced the front by increasing tube thickness, bracing the main hoop, and adding 2 members. Revision 2 reinforces a shock mount member in the rear, and Revision 3 braces the seatbelt harness. After running each revision through both load cases, we found that the chassis never yields from these cases. Revision 2, which reinforced the shock mounts, provided the greatest improvement to weight ratio by decreasing the max stress by 18.3%, as well as deflection by 3.7%, 1.7%, and 88.5% in the front, mid, and rear of the chassis, respectively, with a 2.4% increase in weight.
While braking, the brake rotors will generate heat due to friction while trying to decelerate the race car. To account for the thermal loads and heat generated, we ran a thermal analysis. The brakes are made from a gray cast iron material and were fixed along the inner circular surface with a circumferential force and pressure applied on one side of the brake rotor. In addition, the brake rotor has a roller boundary condition in order to account for the brake pad. These forces were focused on a split line that indicated the area where the rotor is in contact with the brake pad. There are 2 test conditions that were conducted. The first test applied common loads caused from brake pedal pulsation. The second test applied an average force from a driver with maximum pressure. The first revision took the OEM part and added 12 holes evenly distributed in a circular pattern in order to reduce material and weight. The second revision took the original part, filled one of the middle holes, and extended the 6 slots. From our results, most of our revisions caused higher stresses and temperatures, which was not beneficial since the rotor yielded. However, what did improve were the factor of safety values, with the Rev 2 design improving by over 100%. The original design experienced the lowest stress of 260 megapascals, which means that the rotor can undergo 62,340 cycles before yielding.
For the front upright, the static study will consider forces on the tire contact patch. The first iteration only has the top and bottom mount set as rigid fixtures. Remodels to emulate the locational loads on the tire to the upright will be applied respective to the direction of the maximum possible lateral, longitudinal, and vertical loads, leading to 2 studies. The upright, made of 6061 T6 aluminum, was redesigned to have a lower max stress and displacement as well as higher factor of safety. The second iteration refined boundary conditions by adding a rigid fixture to the tie rod mount and redesigned extruded cuts. More material and a fillet was added to decrease bending and max stress at joints and support sections. At the expense of slightly increased mass, the upright was reiterated to have a max stress of 82.35 megapascals after comparing the lateral static study and the longitudinal static study max stress values. According to the fatigue curve, the upright will last for 10,000 cycles before failure. For the closed form solution, the upright was fixed like a fully fixed cantilever beam. The frictional lateral force of 1,779 newtons is applied to the inner diameter of the center hole. The upright was simplified to the annotated dimensions for the theoretical calculations of max stress and displacement. When comparing the values to the FEA values, there are significant percent errors due to the simplification of the upright component, but the values are still within reason.
The battery box, made from 5052 aluminum, houses the power source of the car. The way it is mounted on the car determines its boundary conditions when we do a modal analysis on it. In the first 3 iterations, you can see how it is fixed at the hinges, because that's how it would be attached to the car. Fixing a surface would then mean attaching that face to the car's body as well. Looking at revision 1, taking out some inner components and also fixing the floor of the battery box changed its natural frequency response. But thickening the shell of the box in revision 2 gave us much different results. The surprising thing I learned was how revision 2 and 3 barely have a different frequency response despite adding corner gussets. Normally, gussets help with structural stability, but we can see how little they help in terms of vibrations. When we get track data on how the car behaves, we would keep these responses in mind and avoid hitting those frequencies to prevent something catastrophic. This analysis helps for any future redesign.
steel hub transfers power from the motor to the wheel. We start by having fixed hinges at the lugs and apply torque inside the hub. The first condition is having the 4 lugs tightened, and the second condition has 3 lugs tightened. With the first test condition, we found that the original part did not yield. In Rev 1, we added support between wedges and removed a trapezoidal string from the wedge. This resulted in higher stresses at the support and more weight. In Rev 2, we removed the crossbar and kept the cutout. This resulted in lower weight and higher stress. In Rev 3, we changed the shape of the cutout into a circle. This resulted in a lower stress and weight, but more displacement. In the second test condition, we found the original part to have the lower stress and displacement. We expect low stresses, and the SN curve shows that we have many cycles before the part starts to fail. In conclusion, most of the stress centered around the wedges and throat of the hub. We found that adding a circular cutout may be a vital option.